Ok, stiamo registrando. Sono sharing. Ok, dovreste vedere lo schermo, giusto? Riuscite a vedere il mio screen?
Sì.
Okay. Okay, so we can start. So yesterday we discussed a bit more in detail the features of the quantum electrodynamics, which is the gauge theory of the electromagnetic interactions. We first of all derived the Lagrangian, and then we switched to the perturbation approach by Feynman, which led to the formulation of these very useful final rules that allow to draw Feynman diagrams and to write down the corresponding matrix elements for the various QED processes. And we studied quite in some detail the molar scattering, either from first principles and just by using the Feynman rules. And then we moved to the E plus E minus annihilation process into Muon pairs. And finally, we went very quickly through some examples of other QED processes, and I just showed how to calculate the matrix element and the cross-section. Okay, and at the very end, we discussed about this crossing symmetry, which allows to essentially obtain the matrix element for coupled processes that are processes that can be obtained by simply, for instance, rotating by 90 degrees some diagrams. Okay, having said all that, so yes, up to yesterday, we have considered only the lowest order diagrams. Okay, so the Feynman approach is a perturbative approach. So when you have a perturbation expansion, of course, you not only have the zero order, so the lowest order or leading order, if you like, but of course you have an expansion. So you have several, actually, in principle, infinite orders that you want to take into account in order to make more precise, more reliable predictions. So indeed, for an accurate calculation of the cross-section for a given electromagnetic process, one should, in principle, include all infinite higher order diagrams. Okay. Now, the full transition amplitude of each elementary physical process is given by an infinite series of Feynman diagrams with the same initial and final state. So suppose you are considering, for instance, the molar scattering. Suppose that this arrow corresponds to electron fields. And this is the leading order process that we discussed yesterday. There is also another diagram, if you remember, but okay, this is the leading order. Then you might consider also more complicated diagrams, okay, which have, as you can see, loops inside, which, of course, which corresponds to higher order terms in the perturbation expansion. Okay, of course, these are more complicated processes and also less probable processes for the reason that we will understand in a moment. So. So the total amplitude at a given order is obtained by adding up the amplitudes corresponding to all the diagrams that can be drawn up to that order. Okay, and the complexity, of course, increases as soon as you go to higher orders. Now, as we have seen, for the simple case of molar and bubble scattering, a minus sign must also be included between diagrams that differ only by the interchange of two incoming or outgoing fermions or antifermions, and this is essentially a consequence of the antisymmetrization imposed by the Fermi statistics. So when you sum up diagrams, you have also to consider this. And what I want you once more to notice here that the complexity of the diagram increases as soon as you go ahead in your expansion, but the initial state and the final state particle are always the same, of course. So we are always talking about the same process. Now, the series reflects the expansion of the transition amplitude in powers of a small parameter, alpha, and this is indeed the sense of the perturbation approach. And the order of the expansion reflects the number of vertices, each contributing square root of alpha, as we've seen yesterday. Okay, so square root of alpha is essentially the vertex factor, so the probability associated to each vertex. The more vertex you have in your diagram, because it gets more complex, the more you have to essentially reduce your probability each time by a factor of square root of alpha. So for instance, LO stands for leading order. A leading order, we only have 2 vertices, and this is, for instance, the case that we studied yesterday, either the molar, the BABA, the annihilation. So these are only 2 vertices, and so the probability is the product of twice square root of alpha, that is indeed alpha. Okay. Now, suppose you go to the second order in your perturbation. Now you get 4 vertices, and let me go again back here. Okay. So all these guide diagrams here have 4 vertices. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So all these diagrams contribute to the second order of our expansion. Then, of course, we might have many more diagrams contributing to the third order, fourth order, etc. Okay, and each time you have to add a square root of alpha per each additional vertex. And this, of course, kills essentially the probability for that process, because alpha is a very small parameter. Okay, so the higher the power you have, the smaller the contribution of each higher order term. Now, the small parameter is, as you already understand, the dimensionless fine structure constant, alpha, or alpha EM, if you like, okay, which, when measured at low energy, is of the order of 1 divided by 137, as you know from quantum physics, from quantum mechanics. And this we can write in whatever system of units, okay? So in the international system, we have it in the full glory. In CZS, it is much simpler. And then in natural units, it's just e squared divided by 4 pi. So we will keep stay on these units. Now, why do we call this the fine structure constant? The name derives from the fact that it determines the size of the spin-orbit splitting in atomic spectra, the so-called fine structure that you know pretty well. But more fundamentally, alpha represents the coupling constant that specifies the strength of the interaction between charged particles and photons. Indeed, it is the strength at each QAD vertex. Now, since alpha is indeed much smaller than 1, the series converges rapidly. And in practice, only few lower order processes contribute to a non-negligible level. Okay, so the smallness of the QAD coupling constant, which is alpha, ensures that you already have a quite precise prediction already at the very first order, and all the higher order can be neglected to a very good approximation. Okay, so essentially the series converges very rapidly in this sense. So the dominant contribution to the cross-section or to the decay rate, okay, corresponds to the leading order diagrams, also known as the 3-level diagrams. And each subsequent order in the expansion corresponds to an additional vertex in the diagram, so contributing square root of alpha, and thus to a probability that is smaller by a factor of alpha, okay? Because then you have to take the square of the matrix element, so this becomes alpha. You have to take the square of this. And so your probability becomes smaller by a factor of 1 over 137. And in practice, QAD calculation at 3 levels, so a leading order level, are already accurate at the level of 1%. Okay, so you already make very, very reliable predictions if you stop your expansion at the lower, at the leading order, at the very first level. Now, it turns out that the fine structure constant, so the electromagnetic coupling constant, alpha, is not actually a constant, okay? But it is a running constant. This means that its value is not constant, but depends on the energy scale. At low energy, its value is the well-known 1 divided by 137. But if you increase energy, the value of alpha increases, okay? And for instance, at the scale of the Z0 mass, so when we are at the order of 90-100 GeV, the value of alpha has increased now to the value of 1 divided by 128. So it is not a constant, but it depends on the energy of your process, okay? Now, this, however, brings us to a problem now, okay? So before going on, let me just repeat the sense of all this. So your problem is you want to make the most possible reliable prediction for your QAD process. So you want to take into account all possible higher order contribution to your matrix element. Then, of course, you can neglect the very high order because these are very negligible because they come with a very high power of alpha. Nonetheless, you want at least to have the first order corrections, this one here, okay? However, this brings to a very fundamental problem, and I will try to show you now. So a serious complication arises when dealing with higher order diagrams. In fact, it turns out that the theory is intrinsically divergent at large momenta. This is called the ultraviolet divergence. And obviously, a divergent theory cannot describe a real physical process. So indeed, until a solution was found, okay, the entire reliability of QED was put under serious doubts because of this. Okay. Now, the solution, which is known as renormalization, was first proposed in a covariant formulation by Schwinger, Tomonaga, and Feynman, and this is essentially the reason why they got the Nobel Prize. However, their approach does not work for the strong interaction and the weak interaction. It only works for the electromagnetic interaction. But then a more general approach was proposed by Gerard 't Hooft, who rigorously demonstrated that a spontaneously broken Yang-Mills theory is by construction renormalizable. Okay, so for the moment, let's forget about the meaning of this. Okay, this will be maybe clear at the end of our course, okay? But nonetheless, this is a general proof, okay? And this new approach could be then successfully applied also to the strong and weak interactions. And indeed, it constitutes the basis of the modern gauge theories, so the standard model. Now, the proof by 't Hooft is extremely complicated and goes well beyond the scope of this course. So what we will be doing now is instead to just analyze a simple case of divergence in QED, and I will try to give you the essential idea of renormalization. Okay, the formal proof we will completely forget. It's beyond the scope of this course. So let's consider, for instance, a scattering of an electron with an atomic nucleus. So a Coulomb scattering mediated by a virtual photon. Okay. At first order, this will be just mediated by a single photon, okay, with its standard propagator. Now let's consider a higher order process, like the one you see here, okay? So where now the virtual photon, which is exchanged between the electron and the proton, or the nucleus, whatever, splits into a E plus E minus pair, okay? Which are then again reabsorbed into a photon, which at the end goes to the nucleus, okay? So this is a higher order process because we have now two additional vertices, one here and one here, where our virtual photon essentially decouples into a virtual pair of E plus, E minus, which are then reabsorbed in the time allowed by the uncertainty principle, of course. Okay, so all this is, of course, allowed by the uncertainty principle. Now, this loop diagram requires an integration of the E plus E minus propagator over the loop for momentum P. So there is a for momentum P, which is running in this loop. And for the reason that we will understand in a moment, we need to integrate the propagator of this E plus E minus object over this for momentum, okay? And then we have to add an extra factor -1 to the n for each fermion loop. So just n equal 1 in this simple case. Why do we need to integrate over the momentum? So the reason is the following. So although, of course, for momentum is conserved at each vertex, the momentum P, which circulates around the loop, is completely unconstrained, okay, because it is all virtual here. In principle, it can take any value from 0 to infinity. And since it is not observable, because it is a virtual, we have to integrate over all possible values of this for momentum. Okay, so we need to integrate our for momentum from 0 to infinity, the for momentum that is circulating here. So this is how the matrix element for this process would look like. Okay, so here we have the standard current at the upper vertex, the one that we learned yesterday. So we have the adjoint spinor for the final state electron, the vertex factor, okay, where E corresponds to square root of alpha, of course. And then we have the spinor for the incoming lepton. Then we have the propagator for the exchanged photon, this guy here. Then we have the integral over the four momenta of the E plus E minus propagator, okay, which corresponds to all these objects here. Then we have again the photon propagator for the, let's say, final state photon, okay, after the plus and minus are recombined. And finally, we have the vertex factor at the end, okay, including the charge of the atomic nucleus. Now, what is the problem? The problem is that this integral diverges logarithmically at high momenta. So when you go now to plus infinity, this integral diverges. Okay, and of course this is a serious problem, because a diverging theory is a theory that cannot describe real processes. So something is wrong and something has to be adjusted here. Okay. Now, a solution can be obtained by introducing a so-called cutoff parameter m squared that replaces the plus infinity at the upper limit of integration. So let's put, instead of plus infinity, let's put m squared here. Okay. This is nothing magic at this point, because then, of course, you solve your integral now from 0 to m squared, and then at the end you let your m squared go to infinity. Okay, so it's just a mathematical trick, but there is nothing special. So the infinity is still there. Okay. Now, once you do so, you can now calculate your matrix element. Okay, you find the full passages in Alze-Martin. If you are interested, I will not care about the passages. Let me just draw the result. Okay, so again, you have the same current here. We have the same vertex factor at the end. And now, once you solve this integral, this is how the propagator will look like. Okay, where still we have the infinity inside, okay? Because m squared still must be extended up to plus infinity. So for the moment, it's just a simple substitution, and we have not done anything to cure or to mitigate these divergence, okay? Now the magic arrives, okay? So now the trick to eliminate the divergence, and this is indeed the meaning of renormalization, the sense itself of renormalization, consists in redefining the coupling constant E that you find here everywhere, okay, that we call the bare electric charge, in such a way to absorb the logarithmic divergence. So in other words, we redefine this parameter E that we call the bare electric charge in such a way that in the denominator we have now another infinity. So overall the infinity, when you put this to the square, will disappear. But now in terms of a new object, which we call the renormalized electron charge. And the magic of all this is that you get two things at once. First of all, in this way you eliminate your divergence, because you have an infinity in the numerator and also in the denominator. And then you define a new object, which is the renormalized electron charge, which is the one that corresponds to the physical, measurable electric charge of the electron. Okay? Let me try to clarify this better. I understand this is not trivial at all. So, okay, when you substitute this here, okay, the infinity cancels. Whatever value you get your m squared. So with this definition, the matrix element now will look like this. Okay, so we don't have any more any infinities. The divergence is solved, but now everything is written in terms of this renormalized electron charge. So the divergence has now disappeared by construction, because it is absorbed in the redefinition of an unmeasurable quantity, and the theory is now said to be renormalizable. That means it is able to describe physical processes at all orders in the perturbation expansion. So let me summarize, okay, because this is, of course, a quite complicated subject. So what we have done. There is, in general, a set of bare physical parameters that are divergent, such as the coupling constant, the charges, or the masses. However, these bare parameters are unmeasurable, okay? And these divergent parameters can therefore be chosen in such a way that they cancel against the ultraviolet infinities coming from the loop diagrams. And once this cancellation is operated, we are left with the physical renormalized, or if you like, dressed parameters that are indeed finite and measurable. For instance, this renormalized electron charge is the one that corresponds effectively to the charge of the electron, -1.6 × 10⁻¹9 Coulomb. Okay. A remarkable result of the renormalization procedure is that the renormalized coupling constant, the electric charge in this case, are not actually constant, but their value depend on the energy scale. And for the reasons are in general called running constants. This will be clarified now in the next slides. Let me first of all continue with this approach, and then we may make some try to clarify if something is not clear. So there is one more problem, because we've seen that the infinities arising in the loop of the diagram A can be cancelled by a proper redefinition of the electron charge. Okay, this is the renormalization. Now, since the loop regards the photopropagator, this redefinition of the electron charge is independent on the type of fermion. Whatever you have here, electron, muon, tau, quark, doesn't matter, because the renormalization process is done here on the photon propagator. Okay. However, one can have loops like this. Okay. So this is not the case for diagrams like this one, okay, where now the loop include the scattered lepton. And so it then appears that we shall get different redefinition of the electron charge for different charged leptons. And this will be, of course, a serious problem, because we know that experimentally the electric charge of the electron, the muon, the tau is exactly the same. Okay. And now another magic appears, okay. This is called the Warn identity. So it can be shown in quantum field theory with a full calculation that the modification of the charge introduced by the diagram B is exactly cancelled by the modification introduced by the two diagrams C. So if you also include in your calculation these two diagrams, okay, where the loop attack either the incoming or the outgoing fermion, then the difference in the redefinition of the electron charge for the different leptons completely cancels. And this is done at every order. So therefore, it turns out that only the vacuum polarization diagram A is the responsible for the modification of the charge, and it does in exactly the same way for all leptons, electron, muon, and tau leptons. Okay. So this cancellation is called the Ward identity. It is a consequence of the gauge invariance of QED. So it is, of course, very complicated to show this formally. And the very powerful thing is that it occurs at every order in the perturbation theory. And this makes, of course, QED extremely powerful. Okay. So in a sense, with this renormalization trick, we are safe, because this applies together with the Ward identity at any order in our perturbation expansion. The renormalizability is a basic requirement of any fundamental gauge theory. A non-renormalizable theory is either wrong, so not physical, or an approximate theory, in the sense that it describes some physical process under some approximation or in some energy limit or whatever, okay? So it's not general. And renormalizable theories constitute only a small subset of possible quantum field theories. And here you see some relevant examples. So QED, it is indeed a renormalized quantum field theory. Also, a massless non-abelian gauge theory, such as the quantum chromodynamics, is a renormalizable theory. Also, spontaneously broken non-abelian gauge theory, like electroweak theory, that will be studied at the end of the course, is also a renormalized theory. Okay. However, there are many examples of non-renormalizable quantum field theories. The fourth fermion interaction, which is the original Fermi theory-weak interaction, as we will study. This is not renormalizable. Massive vector non-abelian theory, quantum gravity, supergravity, etc. Okay. So the renormalizable quantum field theory is only a small subset of all possible quantum field theory that one can think of. But these are the only one that can make a general description of a real process. Okay, because they don't have ultraviolet divergence at any level in your expansion. The renormalization of QED is based on a proper redefinition of the electron charge. But although this may sound as a simple mathematical trick, there is a physical justification. And now let's put some our foot on the earth. Okay, we were fluctuating in this hyperspace, but now let's put some our foot on earth and try to see how this can be also observed experimentally. First of all, you have any questions?
No, I think that was the only one I had was related to what you're going to explain, I think.
Yeah. Okay. So let me just emphasize that I gave you just a very simple example and without proof, just to give you an idea. Okay. The renormalization stuff is a very complicated thing that is done on the framework of quantum field theory. So I just want to give you the idea, okay, the sense, but also I will now show you how this can be even touched experimentally, okay? So it is not completely abstract. It's not just a mathematical trick, indeed. Okay, so if there are no questions, I will continue. So let's consider an isolated electron, okay? A free electron. Now, within the uncertainty principle, the electron can always irradiate a photon, okay, and then reabsorb. But it can also happen that the photon, meanwhile, generate a pair of E plus E minus, which is then reabsorbed into the photon, and then the photon again absorbed into the electron, okay? So these are spontaneous quantum mechanical effects that occurs every time, okay? You can, of course, have even more complicated loops here, okay? This is essentially the first level only. Now, I want to address your attention to the fact that we start from an electron, okay? But then for a certain lapse of time, we have also an electron-positron pair, okay? And then you can also emit other photons, okay, in other directions. And so the net result, okay, is that essentially your electron will be surrounded by E plus E minus pairs, okay? And this, of course, fluctuates over time because this happens in the time allowed by the uncertainty principle. So you create, you destroy, you create, you destroy. Overall, it turns out that in average, your electron will be surrounded by E plus E minus pairs, okay, due to this quantum fluctuation. Now, of course, either the real electron or the virtual E plus E minus pairs, they are all electrically charged, of course, okay? And due to electrostatic attraction, the virtual positron, so those one in reds, are attracted by the negative electron, the negative charge of our real electron. And so they tend to be closer to the original electron than the virtual electrons, which are instead repulsed, okay? And so what we say here is that the vacuum becomes spontaneously polarized. So we talk about the vacuum polarization when we have this kind of effect here, okay? In the sense that these virtual pairs, E plus E minus, are not distributed uniformly in space, but due to Coulomb attraction or repulsion, they tend to be distributed in this way around our original electron. So what is now the net result of this? The result is that the positron cloud partially screens the bare charge of the original electron. So we talk about charge screening. So if we want to measure the electron charge using a probe charge, the result will depend on how deep the probe charge will enter the cloud. Is that clear? This is more clarified in this slide here. Okay.
Excuse me, Professor.
Yes.
I have
Yes.
a question. If the processes of the pre-production of E plus and E minus lives in the time allowed by the uncertainty principle, this time, is it proportional to the rest mass energy of two electrons? By the uncertainty principle, I mean.
It is related to the mass of the electron-positron pairs, yes.
Yeah, okay, perfect, thank you.
Yeah. Because of the time energy uncertainty principle,
yes,
of course.
Yes, I was referring to that, thank you.
Mm-hmm. Yeah, indeed. Okay. So now, let me go again to the problem we have. So we have an original electron with its, let's call it bare charge. Then due to this vacuum polarization effect, okay, the bare charge is somehow screened by this cloud of positrons. So if you want to measure the electric charge of the bare charge of the original electron, the results will depend on how much your probe can get inside this cloud, okay? And so let me show this in this slide. Let me clarify this now. So for large distances, this corresponds to law for momentum transfer, of course. Okay, one observes a small electron charge, because if your test charge is far away from your electron charge, then the original electron charge is partially screened by your positron cloud. Okay, you are looking from outside. On the other hand, for small distances, so suppose you can now enter your cloud. Okay, so this corresponds to high Q square. Of course, a higher charge is observed because it is now less screened, right? And suppose that you can go now to the infinite limit. So suppose that you can push your Q square up to plus infinity. This corresponds to infinitively small distances, okay? And so once you do so, okay, the charge that you probe increases up to diverging here. And so indeed, at infinitively small distance, you are now testing your infinite bare electron charge, the one that enters into the renormalization problem. You see? So indeed, the value of your effective charge depends on the distance from your probe charge, okay? And so it's essentially in the transfer for momentum. If you go to infinity, you go to infinitely close, and so you can probe it completely. And this goes to infinity, this diverges. Now, this is a well-established fact also from the experimental point of view, and it constitutes, for instance, the explanation of the so-called lump shift effect that I already mentioned a few lessons ago, and that we'll now see more in detail. So let's consider the interaction between an electron and the charge of an atomic nucleus, which is mediated by the exchange of a virtual photon, okay? Now, due to the vacuum polarization effect, the potential felt by the incoming electron is not exactly the Coulomb potential here, okay? But it includes also higher order corrections that account for the E plus E minus loops in the propagator of the exchanged virtual photon. So in other words, you have to correct your Coulomb potential with correction that take into account these vacuum polarization effects, okay? Now, when Q square goes to 0, okay, so you probe your electron charge from very large distance, the electron probes the static charge of your nucleon, okay, from a large distance, where I put here ER indeed, which is the measurable one. And the interaction is just given by the Coulomb term. When instead the electron comes close to the nucleon, closer and closer, so Q square increases, it penetrates the cloud of virtually plus E minus pair, which surrounds it, and it does sees a larger, or if you like, less screened charge. And this leads to an increase of the effective interaction, because if you see, both terms have the same sign, okay? So the potential, the Coulomb potential is increased by this higher order contribution arising from the vacuum polarization effect. And this can be indeed observed also experimentally in the lump shift effect, for instance. So let me just very quickly describe this effect. So the measurement was performed using hydrogen atoms, Z=1, and the correction term has a measurable effect on the atomic energy levels, and its magnitude can be computed using ordinary perturbation theory in quantum mechanics. So this is the situation. So the resulting energy shift, which is called known as the lump shift, okay, was discovered by this guy here, has been measured between the 2s1/2 and 2p1/2 levels, these two guys here, okay, which are degenerate if the loop contributions are not considered. So at the Dirac level, these are degenerate. If you also consider this higher order effect due to vacuum polarization, then this level is not degenerate anymore. And there is indeed a tiny but measurable energy difference here, okay? And this energy difference, which has been measured experimentally, exactly matches the QED calculation if the higher order corrections are included. So if the loop corrections are included. So this measurement proved that loop diagrams give real observable effect. So it is not just speculative, okay? It has an impact also on real life. We can measure these effects. And actually, the interpretation of the observed lump shift in terms of the vacuum polarization constitute one of the most stringent tests of the theory of QED. Okay, so it is predicted because in theory you have to take into account this vacuum polarization effect, and once you take into account, you can predict the value of the splitting you measured, and it exactly matches. So it was really a huge triumph for the theory of QED. Now, what is the consequence of all this, one of the important consequences of all this story? So a very important consequence of the Q-square dependence of the electric charge, as we've seen here, okay, is that also the coupling constant alpha, which is the square of the electric charge, evolves with the momentum transfer. So as I was mentioning at the very beginning today, alpha is not a constant, but it is a running coupling constant because its value varies with Q-square, as a consequence of the fact that the value itself of the electric charge depends on Q-square. The general dependence of the coupling on the momentum transfer is expressed by the so-called renormalization group equations that you see here an example, in which the coupling is expanded in powers of logarithm of Q-square divided by mu square, where mu is an arbitrary scale. So you take the inverse of your alpha, okay, and you make an expansion in this logarithm. You can have, of course, infinite terms here. So this is the leading order term, you have the first order correction, etc., etc., where mu is an arbitrary scale. We have a parameter here, beta 0, which depends on the number of degrees of freedom for bosons and fermions in the vacuum polarization term. So in the case of QED, there are no photon loops, so it only depends on the fermion degrees of freedom. Now you can invert. So suppose you stop your expansion here. Now you can invert this equation. You can extract now this value here. So the dependence of alpha on the Q square. Okay, and it turns out to be to have this behavior. And this is a very fundamental equation because it tells you how to calculate the value of alpha at any Q square values once you know its value at a given scale mu. Suppose that mu is a 10 GeV square. Suppose that you know the value of alpha at 10 GeV square. Then using this equation here, you can calculate the value of alpha at any whatever Q square value. 100 GeV, 1 TeV, whatever, okay? Now, let's go back again to measurements. So the fine structure constant has been determined at very, very low Q square, okay, in atomic physics experiments. And the value is the one that is reported in all quantum mechanics books. So 1, this is the inverse. So 1 divided by 137, okay? But then a high precision measurement of alpha at the scale of Z, of the Z masses, so 90 GeV, has been made at the LEP, which was the electron-positron collider at CERN, before the Hadron Collider. And so we are now at quite large energy scale, and now the value, as I was anticipating before, is now larger. So it's 1 divided by 128. And this proves experimentally, this is, of course, extremely significant if you consider that the uncertainty is very small, that indeed the fine structure constant, and so the electron charge grows slowly, so logarithmically, with increasing energies, or if you like, with momentum transfer. So this is a plot that I showed you yesterday, if you remember. This is about the Baba scattering. So E plus E minus going to E plus E minus. If you remember yesterday, I told you that let's consider only the full line here, and the data are in very good agreement over many order of magnitudes, okay? So what is now the meaning of the dotted line? So the dotted line is your prediction for this cross-section as a function of the cos theta if you keep your alpha constant to the value 137. Whereas the full line is if you keep alpha running in the way that we just studied, so through the renormalization of group equations. And you see that indeed the data agree only with the second case. Okay, this is another very strong experimental proof that indeed alpha is a running constant. This is another way to see the same thing. So this is now 1 over alpha as a function of Q square. And you see that this is the prediction you would expect for a constant value of 137. And this is instead how the experimental data bend, okay, as soon as Q square increases. This is the inverse, okay? So if you take alpha, this means that it is increasing in value. And the line here, the dotted line, is of course the QED prediction, which fits very, very well the experimental data that we have so far. Okay, any questions?
Yes, sorry, in the case of the Baba scattering, I don't understand the influence over the angle, actually.
This we studied yesterday. If you take the slides from yesterday, we derived the differential cross-section as a function of cos theta. And this was done by using the proper definition of the Mandelstam variable u and t in terms of theta. Yes.
Sure, but how the fact that it's a running constant influence is because we're at the same energy, right? Because we're at the same square root.
Yeah. So this is when you calculate your alpha at the energy of that experiment. Okay. This is if you put your alpha at the log square value, which is 147.
Okay.
So this is the prediction calculated at the energy of that experiment.
Okay.
L3 lab. So it is essentially at the scale of the Z0.
Okay.
Okay. Okay. So so the lamp shift from one side and the running alpha from the other, okay, allows to make very stringent constraints to the theory of QED. So QED make very precise prediction, and then indeed these are all verified experimentally. There is also another observable that allows to constrain to an extremely high level the QED predictions. That is the magnetic moment that we already introduced when we spoke about the Dirac theory, if you remember. So let me just repeat again about this. So precise tests of QED have been performed in many fields of particle physics, and indeed we have just discussed the remarkable case of lamp shift. The most accurate test arises from the measurement, however, of the electron magnetic moment. So if you remember, we defined the magnetic moment in this way, where S is the spin, okay, Q is the electric charge, M is the mass of the fermion or the whatever particle, and G is the gyromagnetic ratio. Then we can, okay, replace the electric charge with that of the electron, minus C, and we can express the spin operator in terms of the Pauli matrices, multiplied by H bar divided by 2, okay? And then we can define the Bohr magneton, like EH bar divided by twice the mass of the electron. So it is all these objects here. And so we can, at the end, express our magnetic moment for the electron as minus G divided by 2 times the Bohr magneton, and then the Pauli matrix. Okay. Now, if you also remember, one of the precise prediction of the Dirac theory is that for a Dirac particle, G must be exactly equal to 2. Where a Dirac particle means a point-like fermion that is a solution of the Dirac equation. Okay? So the Dirac theory predicts that G must be exactly 2 for any Dirac particle. So these cancel in the ratio. So overall, you expect that for a Dirac particle, the magnetic moment is given in terms of the Pauli matrix multiplied by the Bohr magneton. Okay? This ratio just goes to 1. This is the prediction, okay, the pure prediction from Dirac theory. Of course, this does not take into account the higher order QED corrections, okay? So if we now take into account the higher order QED correction, that can, of course, they can be infinite, okay? Then, of course, this ratio is not anymore 1 in units of the Bohr magneton, but you have to include here also corrections, okay? So overall, when you take into account many of these higher order terms, you end up with a ratio that it is not exactly 1, but it is 1.00115969. And this is, I mean, not a joke. I mean, you see, the uncertainty on this level is only on the last 2 digits. So this is an extremely accurate QED prediction. Okay? And indeed, this value was obtained including correction up to the 8th order. So this included calculating 891 diagrams, and also the most significant 10th order terms, okay, as well as electroweak and hadronic corrections. So this is essentially one of the most precise predictions by physical theory, okay? You see how many significant digits we have. And they are all significant because the uncertainty is really on the last two. How can we compare this with experiment? So also the experiment have become extremely precise in this field, okay? So one can really make a one-to-one comparison between theory, so the QED prediction, and experiment. According to the QED, the electron has some anomalous magnetic moment, okay, which is something more than just the Bohr magneton, okay? In addition to the Dirac magnetic moment, indeed. Now, the experimental value is also extremely precise and also extremely close to this precise QED prediction. This is really amazing. Just try to compare these two numbers. All those that are in black are just the same, and the difference is only in the last two. Okay, so it is essentially the two numbers are indeed consistent within the total error, which is the theoretical error and the experimental error. This is really amazing. Consider how many digits we have here. A similar level of agreement between theory and experiment is provided by the Muon anomalous magnetic moment. And in both cases, the results are more commonly reported as the ratio G minus 2 divided by 2. So this is the G minus 2 divided by 2 value expected from QED for the electron and the muon, and this is the corresponding experimental value. So for the electron, we just seen that the two are amazingly similar. We have, at the lower precision, also a very good agreement for the muons. How was this value calculated for the muons? So this QED prediction. So this is another amazing thing. So the people who made this calculation took into account something like 12,672 diagrams. And you see here the contribution at the various perturbation orders. So at first order, you have the main contribution. Okay, essentially most of it comes from the first order. Then we have a sizable contribution on the second order, a smaller contribution to the third order, and then a smaller and smaller, even negligible contribution at the fifth order. Okay, so in order to make such a precision value, they had to compute so many diagrams. A crazy work, of course. But that is what you need in order to make comparison with the experiment, because also the experiment are now becoming extremely precise in this field. Now, a few comments. The leading correction, so let me go back here. This is the leading correction, alpha divided by 2 pi, okay? The first order correction. The leading correction to the three-level diagram is the same for electrons and muons, while the higher order corrections are different for the two, both in magnitude and in sign. And this is a consequence of the fact that the loop corrections are proportional to the square of the respective masses. And those of the muon are much larger. You know, the mass of the muon is 200 times the mass of the electron. Then you have to take this squared, so it makes a very big difference. The sensitivity to loops involving hypothetical new particles, this means not predicted by the standard model, is thus much higher for the muon case than for the electron case. And precise measurement of the muon anomalous magnetic moment turns out to be a powerful tool to test the existence of physics beyond standard model, supersymmetry, dark photon, whatever. So let me stress again now the comparison between theory and experiment for the muon magnetic moment, anomalous magnetic moment. Okay, so indeed the two are not completely equal. Okay, there is some difference here. So let's see now if this difference is significant or not compared to the uncertainty. So let's do the most simple thing one can think of. So let's just take let's just add in quadrature the theoretical uncertainty and the experimental uncertainty. Okay. Once you do so essentially these two guys here. Once you do so, you get 76 10 to the minus 11. Okay. And now you have to compare the 76 with the difference between these 4 digits and these 4 digits. And what you notice is that although they are quite close, so is 1,800, is almost 2,100, the discrepancy is larger than 3 sigma. Okay, so it is larger than 3 times this uncertainty here. This is a total uncertainty here between the theoretical and experimental value. Now, of course, this discrepancy has triggered a wide debate in the physics community that it is known as the G-2 problem. So the question is this significant, statistically significant difference just a statistical fluctuation, or it arises from the evidence, it is an evidence of some new physics beyond the standard model, okay? So the statistics is still limited. So, I mean, we are not at 5 sigma. 5 sigma is, you know, the level of discovery. We are at the level of an evidence, okay? But this is quite an important evidence, you see. Above 3 sigma is quite something, okay? So still, this can be a statistical fluctuation, okay, due to the still limited occurrence in the theoretical calculation. So you want to add more and more diagrams in your calculation. So you go even beyond the fifth order. Or it could be indeed the evidence of some new physics that you cannot explain with your QAD calculations. And where is this new physics possibly hidden? Well, because you have here many loops, okay? So from the standard model, these loops are made, for instance, by E plus E minus, or Mu plus Mu minus, whatever. But you never know that in some of these loops, new particles which are unknown, which are not standard model particles, can also contribute, okay? X plus, X minus, whatever X means, okay? So if you get a significant difference between your theoretical prediction and your experiment, then there could be a hint of new physics beyond standard model, okay? Now, this is a very hot topic, indeed, in particle physics, and new experimental data with an improved precision by a factor of 4 are now expected to come in the next few years from the E989 experiment at the Fermilab, okay? So we will see in the next year if this discrepancy will dissolve into a statistical fluctuation or if it becomes really effective, and so indicating some new physics beyond standard model. Any questions?
For the theoretical prediction, can we automate and go further?
What's the question? Sorry.
For the measurement, I mean, okay, the number of loops that have got to be taken into account is large, but can that be automated just by numbering all the cases and going further down? What's the main problem in having a more precise prediction?
Yeah, the main problem, let me tell you in a very basic way, is CPU time. In order to make these incredibly precision calculation that include so many diagrams, you of course need extremely powerful computer programs that run over parallelized CPUs for months, even years. Okay, so if you want to increase your precision by another order, this means adding something like the 50,000 more diagrams, 100,000 more diagrams, and so on. So the complexity of the calculation increases exponentially each time you go from one order to the other. So it's a matter of time and of CPU availability and essentially computing time. Did I reply to your question?
Yes, indeed. Thank you.
If you let me go back to the very first slide today. You see, this is the first order. All those are the second order. Then can you imagine how many you have on the third order, and how many you have at the fourth order, how many you have at the 10th order, and so on. So the complexity rises very quickly. Okay. If there are no other questions, we can make a 10 minutes break. We can start again at 10 past 12. Okay?
Okay.
Ok, riprendiamo la lezione. Ok, mi confermate che mi sentite e vedete la slide?
Sì.
Okay, so we just completed the third module of the course that was about quantum electrodynamics. Let's now start a new one, which is about spin statistics and the discrete symmetries. So let me just repeat things that for sure you know already. Okay, so all particles, either elementary or not particles, can be categorized into two groups according to their spin. So fermions, which come with an half-integer spin, 1/2, 3/2, 5/2, etc. They follow the Fermi-Dirac statistics. So for instance, they have to obey the Pauli exclusion principle. And what matters now for us is that the total wave function must be antisymmetric for exchange of any identical fermions. The other category is the bosons, which come with integer spin, 0, 1, 2, etc. They follow the Bose-Einstein statistics. So for instance, they are allowed to create Bose condensates. And for what matters us is that the total wave function must be symmetric for any exchange of identical bosons. So let me now move on to the blackboard. Fatemi provare se riesco a fare lo sharing della sola lavagna. Vediamo un po' se riusciamo. Ok, vedete la lavagna bianca? Can you see the whiteboard?
Sì.
Si vede come ieri la dimensione o è ingrandita rispetto a ieri?
È un po' più grande, però forse non so se riesce a zoomarlo, non si riesce, vero? Neanche con Ctrl+.
No. Posso provare, dai, vediamo un po'. No, niente da fare. Vabbè, cercherò di scrivere un po' largo e poi comunque vi passo le scansioni come ieri, ok? Okay. So let's consider a generic system of two identical particles, which are described by a total wave function psi1, 2. So let me write it here. Okay, so this wave function describes a system of two identical particles. Let me now introduce the exchange operator. We can call it I, for instance. And it is such that when you apply this operator to our two particle states, it turns the wave function where the two particles are now exchanged. So psi1, 2 goes into psi2, 1. Now, clearly, if you apply twice the exchange operator, you must recover the original wave function. So let's now apply the squared exchange operator over our wave function. So this is equivalent to apply I to I applied to psi1, 2. So let's first solve the parentheses. So based on the line before, this is just psi2, 1. Then we apply once more the exchange operator, so we'll recover psi1, 2. Okay. So if you now compare the first and the last passage, it turns out that the eigenvalue of I squared must be 1. Okay, by construction. And so the eigenvalues of I can be either plus or minus 1. So in general, one can have that I psi1, 2 can be equal to either plus or minus 1 psi1, 2. This is the eigenvalue equation for this exchange operator. Now, as we've seen from the previous slide, a system of two identical bosons is symmetric under exchange of the two particles, so under exchange of 1 versus 2. Okay, so let's now consider the case of bosons, two identical bosons. So we expect that the psi 1, 2 must be equal to the psi 2, 1 for the case of bosons. Okay. So let's make the full algebra here. So I psi 1, 2 must be equal to psi 2, 1, which is by construction equal to psi 1, 2, because we are dealing with the identical bosons. This corresponds to plus 1 psi 1, 2. So for bosons, the eigenvalue of I is plus 1. Let's now do the same game, but now for fermions. So we consider two identical fermions. In this case, we know that the wave function must be antisymmetric. So 1, 2 must be equal to minus 2, 1. And so again, I psi 1, 2 must be equal to psi 2, 1, which is now minus psi 1, 2, because we are dealing with fermions, which is indeed the minus 1 psi 1, 2. So for the case of fermions, the eigenvalue of the exchange operator must be minus 1. Okay. Let me now change, clear the board. So this is 1, 2. Voila. All right. Now, as you know from quantum mechanics, in general, the total wave function can be factorized into a spatial and a spin component. So in general, we can write down our total wave function as the product of the spatial times the spin wave function. And this, let me just write it in a different notation as psi of r vector times the spin component, which is a function of the spin and the third component of spin in general. Okay. And the spatial component, as you know from non-relativistic quantum mechanics, this we can always, okay, this in general is psi of r theta phi in polar coordinates. And this you can always decompose it into a radial wave function, psi r, and the angular wave function, which is given in terms of the spherical harmonics, right? So epsilon L m theta phi, which in turn can be written in terms of the Legendre polynomial. So this is proportional to psi r. Then we have a multiplicity coefficient, 2L plus 1, L minus m, 4 pi L plus m factorial. And then you have your Legendre polynomial, which is a function of cos theta times e to I m phi. Okay, all this you should know from non-relativistic quantum mechanics. Now let's try to see what happened when we exchange the two particles. So particle 1 with respect to particle 2. Now this exchange, 1 with respect to 2, essentially corresponds to exchanging the spatial coordinates. And one simple way to see this is that suppose that you have particle 1 here and particle 2 there, okay? You may fix your reference frame such that the 0 is in between. So this is minus x, this is x. So if you want to exchange your particle, this corresponds to exchanging their spatial coordinates. Of course, this you want to do in space, okay? So once you do this in the space, you want to move from r to minus r. This, in terms of the polar coordinates, implies that theta prime is equal to pi minus theta. Phi prime is equal to pi plus phi, and the radial component remains unchanged. So from the last part, we see already that psi r prime is just psi r. There is no difference. The difference occurs on the angles, on the polar angles. So let's now see how the spherical harmonics in the exchanged coordinates it looks like with exchanged coordinates. So we write down our epsilon m theta prime phi prime. This, as we've seen, we don't care about the coefficient. It's just proportional to the Legendre polynomial of cosine theta prime e to I m phi prime. Now, let's substitute here. So this is PLM of cosine of pi minus theta e to the I m phi plus pi. Okay, we are just substituting the coordinate transformations. Now, for the properties of the Legendre polynomial, it turns out that the Legendre polynomial of cosine of pi minus theta corresponds to -1 to the L plus m power of the Legendre polynomial of cos theta. Okay, and then about the exponential part, this is nothing else than -1 to the m e to the I m phi. And to see these, let me open a parenthesis here. You can decompose your, of course, exponentially into e to the I m phi times e to the I m pi, and e to the I m pi using the Euler equation is Euler formula is a cosine of pi m plus I sine of pi m, which is indeed -1 to the m, because the cosine of a multiple of pi is always 0. Okay, so let's continue from here. So now we can merge these two -1 coefficients into a single one. So we have a -1 to the L plus 2 times m. Okay, so we are merging the two. And then we have PL cos theta, and then we have e to I m phi. Now, whatever value of m, which is an integer, either odd or even, since it is multiplied by 2, this will always provide you an even number. So it is irrelevant in the exponential. So this is nothing else than -1 to L PL cos theta e to I m phi, which is nothing else than -1 to the L with the untransformed spherical harmonics. Theta phi. Okay? So, in other words, by interchanging the spatial coordinates, the radial component remains the same, this one here, and the spherical components just gets a -1 to the L factor. So we can now merge the two. Posso cambiare foglio? Ci siete tutti? Avete copiato tutti? C'è qualcuno che deve ancora copiare? Direi di no. So we can summarize now our result that when you apply the exchange operator to our spatial component of the total wave function, this is nothing else than -1 to the L psi r. Okay. So this allows us to write down the symmetry of the spatial component. So everything depends on the sign of -1 to the L. So if L is even, okay, then the spatial part of the wave function is symmetric. Okay, L even means 0, 2, 4, etc. If L is odd, then we get a minus sign on top of everything. So this corresponds to saying that the spatial component of the wave function is now antisymmetric. This is, for instance, 1, 3, 5, whatever. So this is about the symmetry of the spatial component of the wave function. But as we mentioned before, the total wave function has also a spin component. Okay, so we have now to study the symmetry of the spin component of the wave function. And let's do this for a system of two identical fermions. Okay, so two identical spin 1/2 fermions. So the spin of two fermions can be parallel or antiparallel and can be combined in 4 different ways to form a singlet and a triplet state. These I think you know already from standard quantum mechanics. So the singlet state corresponds to S equals 0, and also the third component is equal to 0. So we can write down this singlet state for the combined system of the two identical fermions as 1 divided by square root of 2, and then we have 1 up, 2 down, minus 1 down, 2 up. This is the singlet state. Then the other combinations are altogether form altogether the triplet state. In this case, S is equal to 1. The third component can get 3 values, which is +1, 0, and -1. And the 3 corresponding states are chi, 1, 2, 1, 1. So this is the spin, and this is the third component, which is given simply by 1 up, 2 up. Then we have chi, 1, 2, 1, 0, which is 1 over square root of 1 up, 2 down, plus 1 down, 2 up. And finally, we have psi 1, 2 of 1 minus 1, which is just 1 down, 2 down. So what about now the singlet state? Let me take a new page. Posso cambiare? No? Ci siete?
Sì.
Okay, let's consider now the symmetry of the singlet state. Okay, so we have chi 2 to 1, 0, 0. This is the result of applying the exchange operator to chi 1, 2, 0, 0. So you just have to interchange your particles 1 with particle 2. So this is 1 divided by square root of 2, 2 up, 1 down, minus 2 down, 1 up. This you can write exactly in a totally equivalent way just by switching the order of the two. So as 1 down, 2 up, minus 1 up, 2 down. But this is opposite to the original spin component. So it is minus 1 over square root of 2 of 1 up, 2 down, minus 1 down, 2 up. So this is minus chi 1, 2, 0, 0. Okay? And this corresponds to say that the singlet state is antisymmetric. What about the triplet states now? One can show exactly in the same way that instead the triplet states are symmetric. So one finds easily in the same way that chi 2, 1, 1, 1 is equal to chi 1, 2, 1, 1. Chi 2, 1, 1, 0 is equal to chi 1, 2, 1, 0, and chi 2, 1, 1 minus 1 is equal to chi 1, 2, 1 minus 1. And so the triplet state is symmetric. Now, this rule can be generalized, okay, for any even or odd spin, value of the spin. So indeed, the symmetry of the spin component of the wave function is given by the quantity -1 s plus 1. And in fact, one finds that if s is even, then the spin component is antisymmetric. So you put, for instance, s equal to whatever, you get a minus sign here. So the psi spin A is antisymmetric. Is I put a A for this. I'm sorry, I'm overlaying. Sorry, I have to change page. Let me repeat a new page. Okay. So the general rule is -1 s plus 1 s even, then the spin component is antisymmetric. And so let me write it in this way, with an A to indicate antisymmetric. Spin odd, then the spin component is symmetric. And so psi spin S for symmetric. This is for systems of fermions. What about now system of bosons? So for bosons, the state with total even spin are instead symmetric, while those of total odd spin are instead antisymmetric. Just to give you an example, as for bosons now, total spin equals 0, then the wave function is symmetric. Total spin equals 1, it is antisymmetric. Total spin again even equal 2 is symmetric, etc. So also here we can draw a general rule for bosons. That is that the symmetry of the spin component of the wave function is given by -1 to the s. So s even, then the spin component is symmetric. So psi spin s, and s odd, the spin component is antisymmetric. Okay. So once more, the symmetry of the spatial component of the wave function is given simply by -1 to the L. The symmetry of the spin component, of course, you have to distinguish between bosons and fermions. For fermions, it is given by -1 to S plus 1, okay, where S is the total spin of your system of two indistinguishable fermions. And for boson, it's -1 to the S. So we can put now everything together. So we can put again back the spatial and the spin component together in order to determine how the symmetry of the total wave function must look like. Okay, so let me go now back to the slide. Is it clear up to here?
Yes.
Okay. Okay, so let's put now everything together. So let's consider the total wave function for a system of two identical fermions or for system of two identical bosons. Okay. So again, the symmetry of the spatial component is the same for both. It's just -1 to the L. the symmetry of the spin component is different. As we have seen, is -1 to the s plus 1 for fermions and -1 to the s for identical bosons. So we can now merge the two, okay? So for fermions, we have -1 times to the L plus S plus 1. And for bosons, -1 to the L plus S. Now, we know from the Fermi statistics and the boson statistics that the total wave function for a system of two identical fermions must be antisymmetric. So we impose here that this object must be equal to -1. And on the same way, that the total wave function of a system of two identical bosons must be symmetric. So this object here must be equal to +1. Okay? And both constraints are only possible in both cases if L plus S is even, as you can see. So if L plus S is even, everything is determined by this +1, so you get a -1. In this case, you get a plus sign. Okay? So the requirement in both cases that the sum of the angular orbital momentum and the spin must be even. So for fermions, we have two possibilities, okay, in order to have a full antisymmetric wave function. So either the spatial component is antisymmetric and the spin component is symmetric, and this corresponds overall to L plus S even, or the contrary, the spatial component is symmetric and the spin component is antisymmetric. And this again corresponds to the only allowed combination that L plus S is even. And similarly for bosons, okay? In this case, the total wave function must be composed either by a symmetric spatial component times a symmetric spin component, that again correspond to L plus S even, or to both antisymmetric, okay? Questions? Vabbè, sono cose che immagino avete già visto nel corso di meccanica quantistica, in ogni caso le abbiamo ripassate.
Sì, esatto.
Vabbè, per oggi possiamo fermarci qui. Dalla prossima volta continuiamo questo modulo. Sorry, in English. So today we stop here. For next time we will continue module 4 and we will start to attack the discrete symmetries. So parity, charge symmetric, and so on. Okay. That's all for today.
Okay, thank you very much.
Thank you, guys.
Thank you, bye-bye.
Have a nice weekend.
Thank you.
Arrivederci.
Buona giornata.
Bye bye.